months now, and today I would like to go with you into the field of solar energy once again, and would like to give you a very brief introduction into how radiation can be calculated in terms of designing a solar collector, and what is necessary to do so. So as you can see me twice in this in the participants, this is why I also have my iPad here to give you some simple drawings and equations to calculate a certain radiative heat transfer for an example, and that will come in a few minutes. Yeah, first of all, do you have any questions, comments, concerns so far? Okay, perfect. If not, then I go ahead, and please don't hesitate to interrupt me whenever something is unclear or you would like to ask something, and please switch on your microphone and just talk, and this will be the easiest way for me to recognize it. You have some comments or questions. Okay, let's start with this lecture. As you can see, we are almost ready with this lecture. Last week we talked about radiative heat transfer fundamentals, and today we'll use these fundamentals to talk about heat transfer of solar energy. And next week we will wrap up the lecture with this repetitorium. And today we will first go briefly into the fundamentals from last week again. I would like to catch you up a little bit, that you remember what we have done last week, and with that we can go into this example of heat radiation of a heat radiator, and then we talk about the solar energy transmission. Good, so we have some...
Excuse me, sir?
Yes.
I just want to remind one thing, that on 27th we have an exam.
You have an exam on the 27th?
Yes.
Okay, good. So all the international master students have an exam at the 27th?
Yes, not all of them, because we have the thermo exam and it is an oral exam, so we have, like 15 or 20 students, maybe 30 students. I don't know the exact number, but we do have an exam.
Okay. I guess it's not a big problem. So because we have the lecture one day before in multi-phase flows, and this is one repetitorium for the whole module anyway. Yeah, so I will try to give the repetitorium, the total repetitorium on Wednesday in the lecture of multi-phase flows. And then we have this lecture here left. Yeah, maybe we have this lecture here for questions and discussions and so on, but it's not necessary then to participate at the 27th, okay?
Yes, thank you.
I guess this will be the best opportunity. And then let's use the 27th as well for questions for the PBL and the examen and yeah, whatever you want. So if you're interested in and you have time and not examine, then please participate at the 27th. But it will not be mandatory and not any content of the examens anymore. Yeah.
Yes. Okay. Thank you.
Good. You're welcome. Thank you to remind me. I forgot that this point. Okay, anything else? Good. If not, then let's go to the vocabulary once again. We had this already last week, but I guess it's good to repeat. So emission was, I guess, a vocabulary that is now almost clear. The emittance was another important term. Gives the power of emission that is released as heat from a certain body. We have the incident, which means that we have an incidentant metal. You remember our example from these incidentant metal with different colors. So in German it's glühend. We have the incident angle, so incident light. This is einfallend in Germany. Specular means spiegelnd. Probably this is known for many of you. Intercepted means that we have an intercepted radiation. So this is a radiation that is, let's say, catched or aufgefangen by a certain body. Irradiance means the flux of energy that irradiates the surface. It's a Bestrahlung in Germany. Then we have the radiosity, which is the brightness, die Helligkeit. And this is the brightness, the Helligkeit is the optical sense, which means we have here reflection and emission together. And we already addressed last week the black body. This was a system that catches all incoming radiation. So all incoming radiation is absorbed. This is the so-called schwarzer Strahler in Germany. Yeah, so in German, schwarzer Strahler is a black body, and sometimes you find these schwarzer Strahler in textbooks and so on. So this is a black body. Good, and let's directly start with this black body, because I guess it's good to show you a real black body that is used in reality to measure the power of lasers, for example. So here is a patent of a black body, and for the measurement of laser power, so laser power measurement device, Vorrichtung zur Leistungsmessung von Laserstrahlung. And for that kind of measurement, you need exactly such a black body, because you need to know how much watts or kilowatts are coming out of the laser. And to get that, of course, it makes no sense to have just a surface where a lot of light might be reflected directly or diffuse. And therefore, we use this black body. This is a container that is coated with black ink in between, and you see we have here a very rough wall, and we have only a very tiny hole where the laser light goes through. And then we have here the bottom with a certain angle, so that the total radiation that enters the laser is distributed here inside of the system. But you can imagine it's very seldom that laser light exits here this tiny hole, and therefore, let's say, all the radiation is trapped, or the light is trapped here. The laser beam is trapped in this room, and now the question is, if we have a 10-watt laser, and this 10 watt, we focus the laser into these container here. Where will the 10 watts of power consumed? Of course, the only opportunity is that it's consumed inside of the system. So in other words, all the power that is introduced here into this body will be transferred to heat, because this is the only form of energy that can release this body. It's heat. Yeah, and therefore the body is very good isolated here. So this is an isolation against heat loss. So all the radiation is converted into heat, and so we have a temperature measurement here. And with this temperature measurement, we get the temperature of the black body. Here we measure at the top and at the bottom to have an average temperature. And then with the temperature, we can directly calculate the power. Yeah, with Stefan Boltzmann's law, you remember, we will have this in a few minutes again. And we know the Stefan Boltzmann's constants, we know the temperature, and this helps us to calculate how much power we have introduced into the system. Yeah? And you know the Stefan Boltzmann's law is only valid for the black body, but this is a nearly idle black body. Okay? This might help a little bit better to understand this system and why this black body is important. Okay, another point we addressed last week, and I would like to repeat once again, because it was maybe a little bit too fast last week. This was this view factor. So the view factor, you might remember, was the factor that gives us the ratio of how strongly the radiation is catched, is hitting the surface. And we distinguish here between the two view factors. One view factor is from one surface. So this is here, for example, the view factor 1, 2. means we are sitting on this sphere here and we are watching to the second surface. So how much radiation is catched by this body from the radiation that is emitted by this plate here. Yeah, and if we look to that, then we see directly, if we sit here on this ball and we are looking downwards, then we will see in all these directions here, we will see the plate. Yeah, here we will see the plate on the southern hemisphere, let's say, we will see this plate. On the northern hemisphere, we will not see the plate. Yeah, so in other words, our view factor is 1/2. 1/2 of the surface. We see the surface and 1/2 not. So the view factor is 1/2. On the other hand, if we look for the view factor to 1, then we are on the surface 2 and looking to surface 1. And here, if we look in this direction, we will see nearly everywhere, we will see nothing. And only in this very tiny part here of the hemisphere we are looking to, we see the sphere. So this is nearly nothing compared to all the other directions. In other words, this goes to 0 here. Yeah, here the view factor is 0. This means that if we have a very huge surface here and a little bit radiation from this sphere, then nearly nothing will arrive at the surface compared to the large surface. Yeah. On the left-hand side, this is trivial because here we have two infinite plates parallel to each other, so the view factor for both plates is 1, of course. And here it's another special example. If we have two perpendicular plates, and one is of infinity size, and the other one is with a small size here, then let's see this again. We are sitting on plate 1 and we are watching to plate 2. And as you can see, whenever we look in this directions here, we will see nothing. And in this directions, we will see plate 2. So once again, we have the view factor of 1/2. On the other hand, if we sit on plate 2 and watch to plate 1, then because it's so short, even if we look in this direction here, we see nothing. Yeah, and even here in this directions, we see nothing. So this goes to 0 once again. Okay, so this is how it works, and I guess this is a good idea to understand how the view factor works. So sit on the surface of the first digit here and watch into the surface of the second digit, and then think about what will be visible and what not. Okay.
Sir, I wanted to ask that this 1/2, the number 1/2 is just a number. It doesn't mean that we can see only the half of the plate, right? It means
Yes.
that we can see just a small part of the.
Yeah, no, this means that in 1/2 of all the directions you see nothing, and in the other half of the directions you see plate 2.
Okay.
Yeah, this is why we have half of this view factor. We will see an example in a few minutes, and then you will see what this view factor is good for, why we need that. Yeah. But you can imagine it's a wonderful question for our examiner to ask for view factors. Therefore, it's you should check it a little bit. And it's not very difficult, but if you track this a little bit, then you see how it works. Okay. This was a view factor, and then we have these important equations. Additionally, I would like to repeat first of all the net heat flux of a black body. And you remember we have the net heat flux, so the power that is transferred by radiation. And this is the area, of course, multiplied by the view factor, multiplied by the Stefan's constant here, which is 5.6704 multiplied by 10 to the power of -8 watt per kilowatt, watt per square meter, and Kelvin to the power of 4, -4, and we have the power of -4 because in the Stefan-Boltzmann's law, we have here the temperature to the power of 4 in the multiplication. Yeah, so it's this factor multiplied by the temperature to the power of 4, and here we have two surfaces, and we have, because we have the view factor from 1 to 2, This means we have to take into account temperatures of both surfaces. So this is the temperature of surface 1, and this is the temperature of surface 2. Yeah. And if we have not a black body, but a gray body, then additional to the view factor, we have this emittance. And the emittance, you might remember, was a difference between the black body and the gray body, because not the full spectra is absorbed if we have a gray body. And therefore, we have these old German F here, which is a transfer factor. Now, transfer factor is a view factor multiplied by the emittance. This is a transfer factor. So this means that for a gray body with different geometries, we can use these net heat flux. Oh, by the way, sorry, here is a dot missing. See, of course, a dot is necessary here as well. Sorry for that, because it's a flux. Okay, so this was a brief review from last week, and now we had this kind of graphics here that show us the different view factors. So, for example, if we have two parallel plates, then we can calculate this view factor, for example, with this equation. And this shows you directly that it's not always so easy as I have shown you before with infinite plates or with these other examples. Usually, if you have more complicated geometries, then you have also more complicated equations to calculate the view factor. And this is why, on the one hand side, you can calculate it with the equation. Here's the equation for this situation. Or you can look it up from a graph. And here we have a graph. So this is nothing else than this equation. But here we have the view factor. And here we have the ratio of the two lengths A and C. Let's have a look what it is. A is here the width of the plates, and C is the distance of the plates. Now the question is, where is B? And B is here in this different graphs. Yeah, this is B divided by C. So in other words, if you have the geometries, then you can calculate A divided by C, and you can calculate B divided by C, and with these numbers, you can read out here the view factor that comes up. So this is nothing else here than the graphic, let's say, fingerprint of this equation. Okay. And let's see if we can understand what's going on here. So the view factor gets larger if B divided by C gets larger. What does it mean? B divided by C, B divided by C. Yeah, so if gets C smaller and smaller and smaller, then B divided by C gets larger into infinity, to infinity. And of course, if the plates get closer, then the view factor gets larger. Yeah, this is, I guess, not difficult to understand. If the plates go smaller together, then the view factor gets larger. That's what we can see here until the view factor is 1. And another point, we can try to understand this from here. If A gets much larger than C, then the view factor will increase as well, right? If A divided by C gets larger and larger, then the surface gets larger and the view factor will increase. And that is what we can see here, A divided by C. If it gets larger, then also the view factor increases. Okay. So this is how we can use this view factor. And here's another more complicated geometry. Now you see it goes very fast, much more complicated with the view factors, depending on the geometry. So this is the equation here for this situation. And as you can see, also the dependencies here get much more complicated in that case. So you can read it out of this diagram, or you can use this equation here to get this information. And the third example are two parallel circular plates here. And for this situation, we can use this kind of equation here. Yeah, so with the radii from the upper plate and the lower plate, and then we use the ratio between the radius and the distance. Here is r divided by h and r2 divided by h, and with that we can calculate x, and with x we can calculate the view factor, or we can read it out here from this diagram. Okay, so and this is exactly the example that we need for the example that I would like to discuss with you now to show you how to apply these kind of equations. It's from the textbook of Lienard, and for me this was a nice example to show how to do such calculations. So let's assume we have this kind of heater here. So it's a heater that radiates to the partial conical shield that surround the heater. So the heater is of course here at the bottom, and then the heater is radiating heat in this direction. And as you know from a common heater, usually such a heater has a shield to prevent people to touch here on the hot surface, because the heater surface is here 1200 degrees Celsius hot. And let's say we assume the heater and the shield are black, so that we can assume this is a black body. And then the question is now, what is the net heat flux from the heater to the shield? So we would like to know how large is the net heat flux that comes from the heater to the shield, to see how much power the shield has to cover. And this is of course an important information to decide which material the shield has to be made of, for example, or the volume or the mass of the shield, thickness of the shield, and so on. So we would like to know how much watts this shield gets from these heater here, and then we can calculate how the shield needs to be designed. Okay, that's a question that we have to solve now. And you see at the top of the heater here, we have a temperature of 100 degrees Celsius. This is our assumption. The shield opens at the top at 100 degrees Celsius, and here we have 1200 degrees, 10 degree diameter here, 20 centimeter in height, and 20 centimeter in diameter. Any questions related to that?
You have a question. Any assumptions about heat transfer by convection?
Yeah, good question. But convection, we don't take into account convection here at this point. Yeah, because we are interested in the radiation of heat from this point to that point, or to the shield, and we assume that this is, let's say, shielded also against convection from the outside. So what we take into account here is only radiation in this case. But it's a good question. But here we assume we just want to know what is the influence of radiation. Okay, any other questions? But it's a good point. I should add this here that convection is neglected. Thank you. Good. If you have no further questions to that, then I would like to share my my screen here, my iPad screen, and would like to explain you how we can calculate that. And before I share my screen, so this is related to this problem here, because here we have this lower heat plate, and this is the upper plate of the shield. So if you turn this by 180 degrees, then we have this situation, shield 1, and so the heater plate, and here the opening of the shield. But the question is, how can we transfer this situation here to the situation we have here? Because it's different, right? Here we have an open space, and here we have a plate. So how can we bring this together? And that's what I would like to show you now, how we can bring this together. I hope it works. 1 second, please. Let's go here to this slide. Jawohl. So, I have copied here the problem once again for you, that you can see the problem once again. That's what we have as a question. And now let's see what we need. So this is the equation here that we have, and of course at the end we would like to calculate the net heat flux, so Q net, and Q net H minus S, yeah, because this is H, this is the heater, this is H, this is S, and we would like to calculate the radiation that hits here this shield. So H minus S, this is the net heat flux we're interested in, and for that we of course need the heater surface. We need the view factor FH minus S, yeah, because that's we are interested in, and we need the Stefan's constant, and we need the temperatures TH to the power of 4 minus TS to the power of 4. Yeah, the temperature of the heater minus the temperature of the shield. This is the temperature difference to the power of 4, and this is what we need to calculate the net heat flux. So what is it? The question now is, what is FH minus S? And what we are here looking for is not the radiation from here to there, but we need the total radiation that comes from the system minus this area, right? So we can use this here, this area here, and this minus the upper area. That is what we are interested in. So in other words, it's this FH minus S, what we are interested in, is the same than 1 minus, and then H, F H minus E, and E is here the upper surface. Yeah. So that's what we need. We need just 1 minus this. And now the question is, what is F H minus E? And for that we can look it up here. Yeah, this is F1 minus 2. As here we have 1 minus 2. This is a radiation that we can calculate with this equation, and this is 1 half multiplied by these x minus square root of x to the power of 2 minus 4 multiplied by R2 divided by R1 to the power of 2. So that's our equation we are looking for. And now we need x, and x is here defined, as you can see in the equation, 1 plus 1 plus R 2 to the power of 2 divided by R1 to the power of 2. So, and R1 is, as you can see, small r divided by h. So this is obviously 5. Please don't be confused. R1 is here the lower surface, and the diameter is 10. So that we have 5 centimeter divided by h, and this is 20 centimeter. So, and furthermore, so this is 4.25, and R2 is R2 divided by h, which is, as you can here see, 20, so 10 centimeters divided by 20 centimeter, and this means this is 0.5. So, okay, yeah, and now we can calculate x. This means x can be calculated, and with x, I don't have x here now, details brings us x. And after x, with x, we can calculate the view factor and the U factor H minus E is with this calculation 0.192. Yeah, this is a view factor that has been calculated with this equation. So if we have a radiation in this direction, but what we're interested in is the radiation to the shield without this. So we have to use 1 minus. So FH minus S is 1 minus FH minus I, and this brings us to 0.808. And now we can use this value, set it in here in this equation, and so we get Q net. In that case, with that is Boltzmann, the Stefan's constant. I write it down here once again. It was 5.67 multiplied by 10 to the power of minus 8. And so we end up here with a net heat flux of 1,687 watt. And that's the result. So we have 1,687 watt that are transferred from the heater with radiative heat transfer to the shield. Now with that value we can do the calculation. Okay. Any question left to this? I guess it's not very difficult, but I hope it was helpful to see the application of these equations. Good. If you have no further question related to this example, then I would like. Yes.
One addition, just in general, Professor, how to enhance heat transfer by radiation? This example.
Excuse me?
How to enhance heat transfer by radiation?
Yeah, how to enhance heat transfer by radiation? Yeah, good question. Is there anybody online who would like to answer this question? What can we do to enhance heat transfer by radiation?
Maybe we can increase the temperature of the heater more.
Yeah, for sure. Yeah, that's right. Increase the temperature. This is one opportunity, or one second here. Yes, we can increase that. That's true. Then of course the area is an important point, right?
Increase the view factor.
Increase the view factor, of course. That's another point. You're right. Sigma is a constant, right? This is a natural constant. We can change something with the Stefan's constant. But if you think on a practical point of view, what can you do to increase the efficiency of radiation? There is one other point that is unfortunately not addressed here in this lecture, but it's extremely important. Think about, it's difficult to give you an example. Yeah, think about, it's easy to give you an example. Think about a bulb, yeah, a light bulb. Let's say it's a very bright light bulb, and you have the emitter in the light bulb. It's a glowing system, and then you will use this as heating system. And what can you do with a bulb to make sure that most heat goes out of the bulb, of this bulb?
Like a mirror behind the glowing wire.
Excuse me?
Like putting a mirror behind the glowing wire, so like that is going to the other side where you want to focus.
Good point. Okay. Yeah, good point. To have a stronger reflectance. That's right. From radiation that goes in the wrong direction. That's right. We'll talk about that in a minute again if we talk about the solar collector. But there's something else. But maybe we can go forward in the lecture first, and we can come back to this question later on. Okay.
Sir, I have another question.
Yes.
So here to calculate the Q net, we need the area, but since it's not given, we have to calculate it separate, correct?
What do you mean with separate?
I mean, it's not given to us, right? So we'll just have to find the area ourselves before we can use it in the formula, right?
Yeah, but here it's given, right? Because we know the size here. This is a
right. Yeah. Mm-hmm. Okay, so we just have to calculate it from the dimensions that are given to us.
Yes. Mm-hmm.
Okay.
Yeah. Okay.
Yeah.
But by the way, there's another point I didn't mention right now in the equation. You have to take care. These are temperatures in Kelvin. Yeah. So you have to change these temperatures from degrees Celsius into temperatures in Kelvin. So by adding 237 Kelvin, yeah, you know that you come from with 1,200 degrees Celsius. These are 1,473 degree Kelvin.
Yeah.
Okay. Good. Further questions or comments?
There is one answer in the chat, I think. If you want to increase the.
Thank you. Yeah. Make sure the objects are black. Yeah, very good point. That's right. Benjamin Branker. Black is important. Otherwise, we have also some losses by radiation through a green to a gray body. That's true. Yeah, but there's another point that is very important if you would like to have the strongest radiation that is possible. And maybe that someone gets the idea during the lecture, then please interrupt me and give me the answer. And if not, then we will discuss this at the end of the lecture once again. What is an important point to have the strongest radiation? Okay, so
that medium player, or
yeah, what do you mean with medium?
Yeah, it could be a vacuum, or it could be a gas, it could be a solid surface.
Yes, exactly. That's it. Yeah, you're right. Yeah, the vacuum is of course an important point, because if you have air, then you will have a strong convection as well, and of course the air molecules will also work as a resistance against radiation. Yeah, so you're right. This is an important point, that the material in between the two, the emitting and the collecting surface, what is in between, this is important. You can also have radiation in water in principle, but radiation in water will probably not very effective, because you have such a strong resistance against radiation, and therefore for the strongest radiation you will have in vacuum, of course. Okay, thank you. So we already solved this problem. So let's talk about radiation. It's a good possibility now to transfer to this topic, to solar energy. And I just want to show you these numbers as a small motivation to go deeper into the topic of solar energy, because there are still a lot of performance that we can use to get our climate change under control. Because if you can see that the sun bestows energy on the earth at the rate of 1.7 multiplied by 10 to the power of 14 kilowatts. Yeah, this is more than mankind has ever used. It's such a huge amount of energy that is transferred by the sun. But unfortunately, the problem is that from all of this huge amount of energy, 1/3 is reflected directly back to space. Back to space from Earth. Yeah, this is one problem. The other problem is that, or let's say, let's start here at this point. So 74% of the solar's energy reach Earth's surface. Yeah, and 30% is directly reflected to space. 9% is scattered at the atmosphere, and 50% is absorbed in the atmosphere. That is what I have just mentioned with air, and we have no vacuum here on Earth. Fortunately, we have air, and this means that 50% of solar energy is absorbed in the atmosphere, and 43% is transmitted to the Earth directly by diffuse radiation. So this is fine, but only 4% of all this reaches the Earth's surface by convection. So this shows that only a small amount can be used, only what is transmitted directly and by diffuse radiation, and what is reaching the air by convection. Yeah, there was this interesting question before for these for the heater, if radiation has to be taken, convection has to be taken into account. Here you can see that convection on Earth, for example, is not very important related to the total energy that is reaching the Earth by radiation. So, and if you look from the Earth, so the flow from Earth back, so that we have a net radiative exchange to the atmosphere. A lot of energy at Earth is evaporated, and also some radiation is directly reflected back to space. Yeah, so that's what happens with the radiation that enters into the atmosphere and hits the surface. So this means that we have, from all these 1.7 10 to the power 14 kilowatts, unfortunately only a small amount that can use by solar collectors. But what is quite interesting from my point of view is you see here we have the diffuse radiation. A lot of radiation hits the Earth by diffuse radiation, and I don't know if someone of you has already a solar collector on the roof and knows how efficient these systems are. I'm by myself always very impressed how much heat these diffusive radiation can produce. So even if we have a cloudy day, a lot of heat enters into into these solar collectors, and can heat up your heating system at home, because even that it looks quite, let's say, with low energy, the diffuse radiation is extremely strong. So this is why these collectors are designed in such a way. So now we know about these important parameters here. We know about the absorbance, alpha, we know about the reflectance, O, and we know about the transmittance at tau. So what is necessary now, if the sunlight, diffusive or direct, hits our solar collector, of course what we want to is that most energy is transmitted into the collector, of course. Yeah, so we will try to avoid that sunlight is reflected. Think about the black body, and we want that not so much light is absorbed, or radiation is absorbed, because you want it in the collector to transfer the solar energy to heat. And this is why usually these solar collectors have certain glass plates that are preventing too strong reflection, as you can see here. But of course we have some energy loss by reflection, unfortunately. And very often we have two glass cover plates on the solar collector. And then we have here the absorber plate. This is usually black painted plate to have a more or less black body that transfers all the energy that enters here into the system into heat, hopefully. And the plates have a second task, and this is that light that is reflected once again, to make sure that we have here such a system that all the radiation is, let's say, trapped in this system, and to avoid that we have heat loss by radiation. And then, of course, the most important part are here these tubes. These are the cooling water tubes that help us to bring the heat away to our solar storage or heating system or whatever. So, and by the way, we're coming back to the point before. Why do we have two plates here? Any idea why we use two parallel plates? Because we have losses by the plates, right? So even by that plate, we have losses. So why do we not only use only one plate? Probably the losses.
So that we can, to cover the losses, yes. So that we can utilize the maximum.
Yeah, but why do we use two plates? What is the advantage of two plates? Any idea?
You could reflect energy once more.
Yeah, we don't want it. We don't want this reflection, right? And you see this.
No, the reflection to the absorber.
Yeah, but this one is much bigger than that one, right? So why do we have two plates? It's a nice example for heat and mass transfer. What is the reason for two glass plates? Maybe you have the same system in your Windows at home. Probably you should have. Probably you have two glasses as well, or maybe three glasses in your Windows.
Right.
What's the reason for that?
Create a void, an empty space in between.
Excuse me?
To create an empty space in between? Or
I didn't get it. Would you please repeat?
to create an empty space?
It's like a vacuum.
Yeah, but
yeah. So Benjamin Brenke mentioned to minimize the convection heat loss, but why is the convective heat loss reduced if you use two glass plates?
Because between these two plates are air is not good cannot good conduct the thermal energy.
Yeah, the point is usually air is a quite good conductor for thermal energy. So not very good, but it's a conductor. So what you usually do is to evacuate this volume here in between the plates. Yeah, and the evacuation here is not on the one hand side you have a lower you have a vacuum inside, so this means that the radiative heat is less absorbed here, yeah, because we have a vacuum. But the much more important point for the vacuum is that a vacuum is working as a resistance against heat transfer. So it's correct what Benjamin Brenke means, that we minimize the convective heat loss, but we minimize the convective heat loss here inside this plate. So this is a very good isolator. Maybe you have at home or maybe directly in front of you right now these isolating cups. Yeah, and you might know that these isolating cups or also isolated coffee cans, they have a vacuum inside. You know, if you look into an isolated coffee can, then you see these silver shining silver shining surface. And what you need to know is that it's a double walled system, and the inside is vacuumed. And this is to prevent convection inside. If there's no gas inside, then you have no convection, and then you have a very good isolation against heat loss. So the two plates and the vacuum is more to prevent from heat loss from the lower part here to the upper part, because we would like to reach very high temperatures here, of course, for the cooling water tubes, but we don't want that energy is get lost here, and therefore we have this isolating double glass plate. Okay. This isolating performance here is so much higher than the loss that we get here by reflections that it's very worth and important to use this. And maybe that you know that there are also vacuum tube solar collectors on the market, and it works very similar. But then we don't have a plate as collector; it's a tube, and this tube is evacuated to even have to come to a higher performance. And the higher performance is indeed higher, but you can imagine these collectors are much more expensive because it's a big effort to produce these vacuumed pipes. Okay, another point that was mentioned was to increase the surface area. Yeah, surface area, of course, is an important point, but you don't increase the surface area with this plate, because what we're interested in is to increase the surface area here for the heat transfer, right? And not here, because this is just a plate that needs to be passed by the radiation. We just need to use this plate for better isolation against heat loss.
I have a question once more.
Of course.
The radiation works from the air to the cooling water tubes, but isn't there the resistance through the vacuum as well?
Not against radiation. Or what do you mean?
So this back is the convection heat. Yes. Now I understood.
Yeah.
Okay. Yeah. Okay. Now I understood it.
You remember sunlight is reaching our Earth because the radiation works very well in vacuum. Yeah. Because in space we have vacuum as well, so the radiation is not hindered by a vacuum, but the heat loss by convection is of course minimized by the vacuum, because if you have a vacuum, there's no fluid inside that can convect, that can transfer heat by mass transfer.
Yes, right. Now I understood. Yes, now I understood.
Yeah, but I see it's a good example to think about all these points. Thank you. Okay. Any other comment or question?
So can we say that we are creating a contact resistance between the two surfaces?
A contact resistance. Contact resistance. What do you mean with contact resistance? You mean that there's no contact between the two? You mean there's no contact between the two surfaces?
No, what we studied about having no medium for the heat transfer before, so there's like a thermal contact resistance.
Mm-hmm.
So eventually that reduces the heat transfer, and
yeah. Okay. You can say it this way, that there's no contact between these two plates, even no contact with any gas in between, and because there is no contact, there's a very good transmission of the radiation. Mm-hmm. Okay. I guess we can go forward. So now we have to think about how to do the calculation in detail here, because you remember, if we think about the view factors, then you will directly see after the complicated equations we had before that it's probably quite difficult to calculate the view factor for this situation here with two plates, with different transmissions and reflections, and all these different difficulties. So the question is, how can we do a calculation for such complicated systems? And for that, we have to simplify first all these systems. And we have to distinguish between other parts of this energy transfer. And what we will use here to do this complicated calculation is we will use the electric analogy for calculating heat exchange. Electric analogy, this means nothing more than we use Ohm's law at the end. Ohm's law, you remember the resistance is the power, the potential divided by the current, and then we can add different resistances by calculating 1 divided by the resistance plus 1 divided by the resistance. So we sum up the reciprocal value of the resistances, and with that we come up to the total resistance. And that is the same what we do here. You will see in a minute that we add all the resistances together, the reciprocal value of the resistances, and this helps us to calculate the total resistance against radiation. This was a small introduction. You will see where we will go for now. So, and this has been invented by Oppenheim. So Oppenheim, 1956, found this opportunity to this analogy between electric circuits and heat transfer by radiation. And so Oppenheim first he defined this flux of energy that irradiates the surface. So this is the energy that irradiates the surface. So what that left surface is H, and H is irradiance, and this irradiance H in the watt per square meter. Yeah, this is that what hits, let's say, that hits the surface. And then we have a total flux of radiative energy that goes away from the surface, and this is the so-called radiosity. The radiosity is the energy that left the surface, and there's the same unit, of course, watt per square meter, and this is B. So we have irradiance, what enters the surface, and radiosity, the power that left the surface. So now we can express the radiosity as the sum of the irradiated energy that reflects away from the surface and the radiation that emitted from it. So this is how we can calculate these radiosity. So first we have ρ, which is the reflectance, multiplied by H. Yeah, for sure, H is what hits the surface, and the part that is reflected is part of the radiosity. And furthermore, of course, we have the energy that is emitted by the black body emission. And here we have the emittance and the black body emitted energy. Yeah, so this two parts gives us the radiosity. And now we can calculate the net heat flux again from any particular surface, and this is radiosity minus the irradiance. Yeah, we already talked about this difference. It is the same that with the radiation that we talked about if we talk about these black body and gray body emissions. So we need B minus, and now we can set in here our equation for B, and then we end up with B minus epsilon EB divided by ρ. So this is the equation again, and now we can rearrange the equation. Then we come to the Q net is this equation here. And if we now assume that the surface is opaque, so we have no transmission. Let's go back here to this. Yeah, if we have no transmission, then we have a opaque surface, so no light goes through. Then we have only absorbance and only reflectance. And if we use this assumption, then epsilon and alpha is 1 minus ρ, and then we can simplify this equation to this one. So then we have here Q net multiplied by A, because Q is the area specific heat flux. If we calculate the total heat flux, if we multiply this with A, then we end up with this equation here for the let's say the difference between irradiance and radiosity. So, and now we come to our analogy between electricity and radiosity, radiative heat transfer. So this is the equation we have derived before. And now if we look in detail to this equation, then you see this equation has the form of Ohm's law. And these EB minus B, this can be viewed as a driving potential. Yeah, so let's say this is our potential of for the electric, so the electric power, the potential that brings us to a certain current. EB minus B. So EB was the power that is emitted by the black body minus this radiosity. This is the difference, and the difference is the potential that we have available for the radiation at the end. And now the question is, how can we see the resistance? And the resistance is these 1 minus epsilon. Epsilon was the difference between the black body and the gray body, as you probably remember. And so this 1 minus epsilon divided by epsilon A, this is proportional to our resistance, to our R. So this is comparable with E. So here this is a heat flux of radiation, and this is so the flux of radiation, and this is the flux of electrons. And the potential here is the emission of the black body minus the radiosity. And here we have as potential the potential for current. And here we have the resistance given by these gray body approximation, these epsilon. And here we have the R as the resistance against the current. And if we use these simplification, then we know how to derive these example here, because now we can say we have two plates that are emitting, and we have in between a radiation, and now we would like to calculate the radiation, and we can now split this situation in different resistances. First of all, let's say we have a black body on the left-hand side, and what changes the black body emission from the real emission of the gray body is these first resistance here. This is shown here with these dashed lines. So the first resistance is 1 minus epsilon A divided by epsilon A multiplied by A1. That is what we just defined as a, let's say, resistance, and this changes our black body to the gray body here, to the real body emission. Then we have some in between the plates, and this is especially here addressed with the view factor. So we have 1 divided by A1 multiplied by the view factor from 1 to 2. This is here in between. Then we have another resistance that changes once again from the realistic real gray body to the black body. So here we have this was epsilon 2, and on the right hand side here we have the black body once again. And the black body's emission gives us somehow like the potential for our current. The current is the radiation that goes through here, driven by the potential, driven by this potential. And then we have this resistance. Okay, so this is a very nice and simple analogy between our radiative transfer of heat and our potential-driven transfer of electrons. Yeah. And you remember EB, so the emission of the black body can be calculated once again very simply by Stefan's constant multiplied by T to the power of 4. Or maybe T1 to the power of 4 minus T2 to the power of 4 multiplied by Stefan's constant gives us direct this potential, and then we only need the epsilons, we need the view factor, and we can calculate the radiative heat transfer between these two plates. Yeah, this clear? This
can you explain the picture once more? I didn't understood it well.
Yeah, of course. So so we have a heat transfer between these two plates, yeah, and what we can easily calculate is the emission of the black body. So this is here EB of the black body of the left-hand side, and this is the emission of the black body on the right-hand side. We know that in reality we don't have emission between black bodies. We have emission between gray bodies, and we have also view factors here in between, because usually we don't have infinite plates that transfer the radiation over the whole surface. And therefore, we need to take into account the resistances. So the resistances between the idle black bodies, and the resistance is on the one hand side here the gray body approximation, because we have some losses here because we don't have a real black body, we have a gray body, and this loss can be calculated with 1 minus epsilon divided by epsilon 1 multiplied by A1 here in the denominator. Is this clear so far? This is a resistance, looks like a resistance, and this changes from the black body to the gray body. And we can do the same on the other side. Yeah, here we have the gray body. The body is this one here. This is EB2. And here in between this dashed line and the body itself, we have a resistance that can be calculated with this gray body approximation. Yeah, so if we look from here to there, then we have just radiation from one black body, a gray body, to another gray body. This is in between these 2 points, B1 and B2. B1 is here at this dashed line, and B2 is here at this dashed line. And in between, we have the resistance that comes from the view factor. And the resistance from the view factor is alpha multiplied by the view factor. That is a surface that is really visible from one side to the other side. Yeah, and we have 1 divided by this because this is from Ohm's law how we can add resistances. Yeah, is it more clear now?
Yes, thank you.
Okay, you're welcome. So this is how we can here heat transfer from one infinite gray plane to another parallel with it. Yeah, this is what we have done now. And the radiant energy flows past an imaginary surface. So this is this imaginary surface that we assume parallel with the first infinite plane, but quite close to it. So this is here in between. And because, of course, no way of telling whether this energy comes from a real surface or a black body, we can simplify this with this gray body approximation here. So that's what we get as equation at the end. And now we can set in this equation here the real equation from Stefan Boltzmann's law. So remember, I just mentioned that EB is sigma multiplied by T to the power of 4. Remember, the view factor for parallel plates is 1, and we assume that both areas have the same size. Both areas same size, parallel infinite size. This means the view factor is 1, and A1 is A2. And if we put the simplifications into the equation we have derived before, then we end up with this equation here for the net heat flux. Yeah, this is a net heat flux. Here we have Stefan Boltzmann for the black body heat transfer, and we divide by all the resistances. This is Ohm's law again. Yeah, this is analogy to Ohm's law, potential and resistances that are added here. And then, of course, we can calculate the area-specific net heat flux by dividing by A. So here we have A, so A can be neglected, and then we end up with this simple equation. Yeah. So remember, you remember we had a similar equation before with the transfer factor here. Yeah, do you remember? It was a transfer factor before. Maybe I can go back here to one of the first slides from last week. Here, yeah, it's exactly the same equation with the net heat flux with the transfer factor. And here in this transfer factor, we have again the view factor and the emittance. Yeah, but this is the very general, let's say, overall equation. for the whole system. But if we want to design a solar collector, then we need to know the heat flux in between the different surfaces that are located in different ways. And therefore, we need these correct orientation of the surfaces, the size of the surfaces, and so on. And then we can calculate with this resistances much more in detail how these transfer factor look like. In this case, the transfer factor looks like this. Transfer factor is easy to calculate here because the view factor is 1. So what is left is the arrangement, let's say the arrangement of the emittances. Yeah, and this is how these emittances are arranged in the case of these two infinite parallel plates of gray bodies, real systems. Okay. Good. And now we can, with this equation, we can have a look on a shield surface. Radiation shield is a surface usually of high reflectance that is placed between the high temperature source and its cooler environment. And if we have this situation, then we see here we have the normal equation that we had before. And if this is shielded, then we have here an additional part for resistances added by the shield. Yeah, so you see we can now, let's say, design our system with the resistances that are added here at certain points in this case, as one example. It's getting now more complicated, and I don't want to go into too much detail here. I just wanted to see that you, in principle, know how to calculate radiation. Probably you will not, during your professional career, have too much to do with that. So, but you should know that radiation is treated in a different way than convection or diffusion, and that it's even not easier, despite the fact one thinks that radiation should be not too complicated. So what you can see here, if we have more bodies, like a three-body transaction, then we can use simplification by these drawings here with different resistances here. For example, we have such a situation, we have a circuit, and within the circle we have two plates that are radiating. So this is a three-body transaction for radiation. And in this case, we have to think about how to calculate this again. So we have here plate 1, plate 2, plate 3, and each plate has its own black body emittance. Here we have plate 1, so this is EB1. So the emittance starts from here. Then we have a gray body approximation as one as well. This is this one here. And then what enters into the room is these B1 here. We have the same at B2, and we have the same from the circuit around it. So this is a black body emission of 3 here, and we have the gray body approximation. And this is then the heat transfer in between these systems. And here only the view factors are important, why we have this the view factors here in between. And now we can try to calculate this in more detail. Again, if one end here is isolated, if 3 is isolated, then we don't have black body emission. We have just B3. So this is an isolated surface at the outside. Now this is how it looks like. You see, this comes now a little bit closer to a solar collector here with this pipe and these different plates. And so it gets more and more complicated if you would like to calculate this. I don't want to go here into details, but you see, you can use this Ohm's law and the calculation of the resistances against radiation, and end up with such equation. So don't worry, we will never ask such kind of things in the exam. It's just for you to see how it works. Okay, so by the principle, you know how to use these equations to approximate the radiative heat transfer in a solar collector. And so in principle, with some training, you should be able to design solar collectors. And here we have a real one. And sorry, as you can see, it's like we have already discussed. We have here the glass plate at the top that is usually coated with a layer to avoid reflection, too strong reflection. Then we have here a second plate. Usually the room between the plates is evaporated to have good isolating situation against heat loss. Then here we have usually copper pipes. Copper is a very good heat conductor with a very high heat conductivity. And you already know from your heat and mass transfer lecture now how to design these pipes to get a nice turbulent flow and to avoid too strong resistance by pressure drop. So probably you have now the knowledge to design such a heat pipe here and to know how long this needs to be, how large the surface needs to be to collect a certain amount of heat. Here at the back we have the isolating layer. You know how to calculate heat transfer and heat loss through different layers, how this looks like. Yeah, so at the end you should be able to design such a system more or less precisely and to optimize it. Yeah, and that's what we have discussed. So we have here exactly the same situation. So here are some hints for designing such solar collectors. So the working fluid needs to reach high temperatures for sure. So that's what we do, and therefore usually we try to focus the solar radiation by some additional shields, for example by mirrors, and very often the collectors are equipped with small parabolic reflectors that focus the radiation on a water pipe, and this helps us to come to temperatures from 100 to 200 degrees Celsius. So very often we have thermal fluids inside that have a higher evaporation temperature than water to transfer more heat through the system. And yeah, what is necessary to produce electrical power is that you have to focus energy in the order of 1 to 1,000. And this is, of course, a much bigger effort. And then just using these solar collectors I have just shown you. And therefore, what can be done to come to such high temperatures and such a high focusing is using mirrors, not around a pipe, but using mirrors and collecting the sunlight into one spot. And this is done here in Spain, in Almeria. This is the Plataforma Solar de Almeria, where solar energy is collected by these mirrors. So these are hundreds and thousands of mirrors, and all mirrors are orientated in a way that the sunlight is hitting the mirror and is focused here in one single spot of this tower. And here we have a high temperature resistance boiler. And in this boiler, water is evaporated and the steam is then used here in a turbine to produce electric energy. This is a very efficient system. Of course, you can imagine it's a very big effort to control all these mirrors because, of course, they have to turn with the sunlight to be always orientated in the direction of this tower here and always to focus the sunlight here in this spot. And I have been there. It's very, very impressive to see how the mirrors are, all the mirrors are, let's say, calibrated here on this white spot. And then if all the mirrors are calibrated in this very, very bright spot, then it turns up here to the boiler. It's very impressive to see, and it's a lot of energy that is collected here from sunlight. By the way, unfortunately, there is one very big problem of the Plataforma Solar. Can you imagine what is one of the biggest problems? So the weather is fine in Almeria. They have almost sunlight there. But what is a big problem by this system? Any idea? What do you think? What is the reason that we don't not have thousands of these power plants?
I think one of the reasons is that this system needs to be washed with water a lot.
Exactly. This is one of the biggest problems. That of course in Almeria you have also a lot of sandstorms and dusty air, and this means that the mirrors are very often covered by dust, and that the efficiency breaks down. This is one of the biggest problems. You're right. And unfortunately, this is one of the biggest problems of many renewable energy plants, also for wind turbines and also for other systems. That sometimes it's difficult to get insurance for them because they are sometimes quite sensible to environmental problems with wind, storms, and so on. This is the same here, that the insurance is extremely expensive, and therefore for the economics it's sometimes a big problem. But anyway, it might be one of the solutions to come to more sustainable energy production and more renewable energies. Okay, any further question to this or to solar energy transfer in general? Okay, if this is not the case, then we are ready with the last lecture. Then I would like to thank all of you once again for participating, for your good questions. I very much enjoyed the lecture, especially the few times we saw us in presence. I'm sorry that it was not more often, but I guess it was an interesting excursus into heat and mass transfer and multi-phase flows anyway. And we will see us next week again for the multi-phase flow lecture. Please don't forget, we will give the repetitorium now only next week on Wednesday in the repetitorium for the module of transport processes in the multi-phase flow lecture. And the 27th here is not a repetitorium. It will be an opportunity for you to ask further questions and to discuss the topics of the lectures and also the PBL and so on. Okay, then thank you so much for your attention today, and I wish you a good afternoon and all the best. Keep healthy, and we see us next week again. Thank you.
Thank you.
Thank you.
Bye bye.
Bye-bye.
Thank you, Prof.
Bye. Bye.